The next series of videos will delve into modern instruments aboard geostationary and polar orbiting satellites, as well as interpretation and application of the data we can collect from these instruments. In the first module, we will look into the instrumentation and wavelength bands, or channels, used on modern GOES and Himawari satellites. The instrumentation on GOES serves multiple purposes. What we will discuss in this class are their Nadir Pointing Advanced Baseline Imager, or ABI, and Global Lightning Mapper, or GLM. We'll discuss the ABI in much more detail, and the GLM in a different module. The top panel shows the size of the solar charging panels relative to the main satellite bus. The ABI, however, is the passive remote sensing instrument that detects radiation in a variety of visible and IR wavelength bands. GLM is a passive instrument that detects emissions caused by the heating of the atmosphere during lightning. Two instruments are solar pointing. SUVI, which is the solar ultraviolet imager, as its name suggests, collects full disk imagery of ultraviolet radiation emitted by the sun at high temporal resolution. EXIS, which can be shown in closer detail in the bottom right panel along with SUVI, is the extreme ultraviolet and X-ray irradiance sensor. Observation of both UV and X-ray radiation can provide some lead time for geomagnetic storms that may impact electrical power grids, radio communication through changes through the magnetosphere, or ionosphere. The Space Environment In Situ Suite and magnetometer respectively monitor ion fluxes and magnetic field variations at the location of the satellite, or in situ. And just as a reminder, the orbit is about 42,164 kilometers from the center of the Earth, or an altitude of about 35,786 kilometers. The distance is shown to scale on this slide, although obviously the satellite size is not shown to scale. The ABI has 16 bands, or channels. This, and the presence of many instruments on other platforms in low Earth orbit, eliminates the need for having a separate sounder that consists of multiple observation bands surrounding some absorption band for the purposes of deriving vertical profiles of water vapor or temperature. The ABI can take a full disk image every 5 minutes, but the default is to take one image every 15 minutes, and in addition collect imagery over the continental US every 5 minutes, and within 1 or 2 mesoscale regions every 30 to 60 seconds. The spatial, temporal, and spectral resolutions are all markedly improved compared to the previous generation of GOES satellites. The 16 channels on the ABI are listed here. The Advanced Himawari Imager, or AHI, has the same bands, except it does not have a cirrus band at channel 4, but has a green visible band at 510 nanometers. I won't discuss every single band right now, but you can use this as a handy reference. Generally, IR bands from channels 7 through 16 have a 2 kilometer instantaneous geometric field of view at nadir, while some of the shortwave bands, or channels 1 through 6, here at the top, have higher resolution. I will often use the terms shortwave and longwave to respectively describe radiation that is either emitted by the sun or by Earth. Each channel observes the spectral radiance averaged over the width of each band, which is indicated in the second column. The higher resolution is possible because of the higher radiance at the satellite sensor in the reflected shortwave bands. In other words, the reflected solar radiation is greater than emitted terrestrial radiation within the same solid angle, which makes sense given the discrepancy in temperature between the Sun and Earth. The width of the bands also controls radiance at a satellite sensor. A wider band will detect more radiation, thereby requiring a smaller field of view to attain enough signal to process. The following imagery shows a sample of full disk imagery for 5 different geostationary satellites. The first shows the disk viewable by GOES 16, or GOES East, centered at 75 degrees west, which views the Atlantic and the Americas. GOES 17, or GOES West, at 137 degrees west, views the western US plus the eastern Pacific. Himawari 8, at 140 degrees east, views the western Pacific and eastern Indian Ocean, as well as Australia, Southeast Asia. INSAT 3 at 82 degrees east views South Asia and the Indian Ocean. It's actually INSAT 3D, and then another one at 74 degrees east is INSAT 3DR. Meteosat 8 is at 42 degrees east and views Eastern Africa, the Middle East, and the Western Indian Ocean. And Meteosat 11 is located at the prime meridian and views Western Africa, Europe, and the Eastern Atlantic. Not shown here are also, as I mentioned, the INSAT 3DR, another Indian geostationary weather satellite at 74 east, and Fengyun 4A, the most recent Chinese geostationary weather satellite that is stationed near 105 degrees east and has instrumentation similar to that on board GOES and Himawari. The current generation of Meteosat and INSAT have lower spectral and spatial resolution than the newer systems, but are comparable to the previous generation of GOES. Together, the satellites provide global full disk coverage of clouds in the tropics and middle latitudes every 30 minutes. In the next modules, we'll focus on GOES imagery before moving on eventually to low Earth orbiting data from the Joint Polar Satellite System, which is a joint effort between Japan and the United States.